Hello everyone, my name is Mario and I'm here to talk a bit about security and how to build basically secure Solana contract programs. You hear me say contract or programs along the way. They are basically the same, but because I basically live in two worlds, actually meant multiple worlds, but two of them being EVM and Solana, I use either contracts or I use programs and so on and so forth. I hope you can hear me well. So let me introduce a bit myself. I'm Mario. I'm a lead security researcher at Cantina, and I've been in security for a long time in my Web2 era. I've did a lot of cybersec and basically moved to blockchain world around 6 years ago, if I recall. I've been with Spearbit from almost the beginning. That's around, I think, 3 years now, or I don't even remember, to be honest. And I've done multiple security reviews for big protocols like, I don't know, Maker, bigger started force in EVM. I did a lot of EVM reviews, and I'm selling out as well of EVM reviews. Yes, so I did like Maker, Euler, and you name it. You can check out my Cantina profile. You can see everything there. In my spare time, I build a Rust-based package manager for Solidity, and because I actually know a bit of Rust, I decided to go in Solana around a year and something ago, and I did a lot of, not a lot, but I did some, if I may say, security reviews for Solana ecosystem as well. Enough about me. Let's go into our material, right? So I'm here to present to you secure Solana programs. Well, this is basically an intro on how to build. I hope I can teach you how to build the first level of security when you build Solana programs. This talk won't cover everything and won't make you 100% secure. There is no such thing like 100%. That's a good thing to know. But at least I hope it's a first step for you to build secure secure programs. These are the topics that I'm gonna touch. I want to first start with explaining a bit what Solana means and introducing you a bit on how Solana works. And then we're gonna go a bit of differences between EVM and SVM. Then we're gonna talk about Anchor, token accounts, PDA, CPI, and we're gonna end up with some common bugs and some real world exploits. I hope this will be useful for you guys. Let's talk a bit about Solana, right? And how actually Solana works behind the scenes. Just a disclaimer, this talk will basically be just a high level, but my goal is to just give you the steps that you need to take into actually writing secure programs, which means that you can take these topics and go in depth because there are lots and lots of stuff you can learn about. Now, going back to account types, right? Solana, a program on Solana consists of a program account, which basically stores executable code, and data accounts, which stores state. For those who are like from Web2, you can think of like program account is like the code you write, and the data account is like the database that stores the state, right? And here in this diagram, we have on the left, we have the program account, and on the right, we have the data account. And as you can see, they're quite similar, but they're quite different, if I may say. This separation is basically different than EVM, and you will see how. For example, we can see that like how this is set up in let's say in Solana code itself, right? This is just an illustration; it's not the actual. Now, how you write this count, but it's just an illustration. You can think of like the data count being like a struct, right, which stores some data. See, as you can see here, we have a counter account which stores a count, which is a uint 32. And on the right, we have basically the program account, which is basically manipulating this account. For example, in here, we just increment. We do a counter data that count plus equal 1. So this is the program account which manipulates this counter account. Okay? No, it's... now let's talk a bit about these differences between EVM and EVM because they're quite different. In EVM, for those who know EVM, the storage basically tied to the contract. Like one contract has a storage, if I may say, that is attached to it, and it can write and read on that storage. While on Solana, the SVM, the runtime, do not allow these read writes arbitrary. Like you cannot write arbitrary GRU accounts that you do not want to. This, and basically, it's a bit more secure than the EVM because it's up to your way of writing these programs on what exactly account you want to manipulate or like read and so on. Sorry. The EVM, as I said, that has storage rows attached to it, right? To the smart contracts. EVM doesn't have that. The data lives in separate accounts, and the programs itself, where you see the code, they don't retain the state internally. They are basically stateless. This means that the security hinges on carefully validating these external accounts. And we will see how important it is validating. If I may say, it's one of the most important things when you write Solana programs. Like validation, it's the key to write secure programs. There are basically two ways of writing smart writing programs. One is you write raw Solana code. The other one is, and it got quite popular, and I think it's one of the most used right now in Solana, is using Anchor. What is Anchor, right? Well, Anchor is a Rust-based framework, which is designed basically to streamline the development and help you, like the programmer, the one who writes the code, to write just a bit more, and a bit more secure and efficient programs. But why and how? If you want to understand, you need to understand that Anchor does not offer 100% security, but it actually gets a lot of things done for you, and you don't need to deal with that. How is doing that? It's basically abstract. It abstracts away lots of boilerplate code that you have to write. It uses these Rust macros and traits to structure programs, manage accounts, validate transactions. So it eliminates a lot of boilerplate that you have to write over and over and over again. For example, in Anchor, you can just with a few, defining a macro, it will actually help you to verify an account constraints right away and not writing a lot of boilerplate code and so on and so forth. We're going to see how this actually works. Here it's an example of, on the left, we have basically raw Solana, but on the right, we have Anchor. And probably you can also see that the Anchor on the right, it's way more declarative, right? Because it's a declarative framework. It helps you actually understand what you are doing, and it's way easier, and it has a lot less code than writing raw Solana. we're gonna focus on Anchor towards the presentation. I'm not gonna enter a lot in the Solana raw, um, in like raw Solana. Apologize. Raw Solana code, because that's a bit more. I mean, there are lots of stuff to talk about there. So I'm gonna focus only on Anchor. Let's talk a bit about like how you init an account in Anchor, right? And with this example, you will basically understand why Anchor is so powerful, right? This is like an usual the initialization of an account. You can see it has some fields defined and some macros like account, init, payer, space, mute, and so on. And we're gonna go step by step and understand exactly what Anchor does behind the scenes. For example, let's get the first sheet, which is the counter, pub counter account, info counter. What basically this does, right? It specifies an init which it tells to Anchor that this account should be initialized. A payer who basically pays off this account in LAMP ports for this account creation, because in Solana for every account you have to allocate some space, you have to pay for it, and that's what basically you specify here in Anchor. And the space, of course, it tells you how much you need to allocate for this account, because if you have a big account, you have to pay a lot of LAMP ports, aka Sol, but if you have a small account, you have to pay accordingly, right? On this account, we'll basically have just 8 bytes, which is a discriminator. This is for all the accounts, and then 4 bytes for the U32 count, if we remember. So in just like 2 lines, we basically wrap a lot of boilerplate that you have to write in raw Solana. You tell to Anchor that to key this account, and you don't need to, care about anything else. But now you look at this account info counter, what exactly this means, well, this actually is a very powerful Anchor, let's say, a feature, because it deserializes the account data into counter struct. So it automatically deserializes it. You will have to deal with that. It verifies that the account is owned by the current program. Very important feature, especially for security, from a security point of view. It handles all the references lifetimes with that info lifetime parameter, and basically provides a convenient access to the account's data and metadata. So in your instruction, like when you actually manipulate this account, you just access it as you instantiate a new object in Rust, simply like that. You don't need to care about any deserialization or anything else. Anchor will manage that for you. As you can see, this saves a lot of code that you have to write. And also in raw Solana, you will have to do like this deserialization checks and so on every time you have to access that account, which of course also means it can introduce a lot of issues. Going to the next field, user signer and a mute there. What that means? Well, mute basically means that the account is mutable. It marks that account data will be written or modified. You may think like, but we don't modify the user signer, right? Well, we do, because we have to pay for the account initialization, the pair its users to the LAMP ports of that account are different. The signer, it's another important, let's say, Anchor feature, which means that this account must basically this wallet user must sign the transaction. So this is a very important thing to notice. Now you may want to think like, why don't we have mute in the counter? Because if you say that mute means that account is mutable, also the counter is mutable, right? Well, init does that for you. So again, another cool feature about Anchor is that it also extrapolates a lot of boilerplate that you have to write in Anchor itself. So you don't need to specify mute for the counter because init will do that for you. Let's go to the last one, which is a system program. Well, this needs to be included because the system program, which is raw, which is native to Solana, is required to create the account, allocate the space, and so on and so forth. So you have to specify that as well. So this is like a normal. Of course, there are many other options here in this, let's say, math rows in Anchor and so on and so forth. But I just wanted to explain this like small example to understand exactly how powerful it's Anchor and how much boilerplate code it actually strips for you. We talked about data accounts and program accounts, right? But probably if you read a bit about Solana, or if you know a bit of Solana, you also know about the token accounts, right? Like, wait, this an account itself. Well, it's a special account type that basically was built by Solana team to illustrate a fungible token. This basically tracks individual ownership and balance of a specific token. Within a Solana ecosystem, you will see a lot that we refer to tokens as mints, right? And that's why here I wrote specific token in parentheses mint. Each token account has built-in features like holds only one type of token, so one mint per account, has a single owner, you can have multiple owners, and stores the current token balance. These are like basic features that were built in these token accounts. And with this, you can express lots of fungible and non-fungible tokens. We will see in the next slide. Up first, the token account was called SPL. This SPL is now legacy SPL token. Why? Why is that? Because this was just the original standard for fungible tokens of Solana, right? It had quite some limited functionality, like basic transfer. I mean, limited but very useful transfers, minting, burning, authority management, and so on. You could not have advanced features like transfer hooks, fee on transfer, like interest billing tokens, metadata, or other types of features. Later on, a new standard was built, which is called Token 2022. This was basically an iteration over the SPL with more dense features. It expanded the SPL token capabilities, and it had the security as well because it added a lot of, let's say, extension. That's what they are called. A lot of extensions that could basically build powerful and richful applications around them. Now we support confidential transactions, metadata embedding, interest-bearing tokens, customizable transfer hooks, fee on transfer. So we have all of these extensions that we can work with in this standard. So you can research them more, but you will see that most of the people are now using Token 2022, and most of the programs actually using Token 2022 nowadays. But there are still some legacy SPL tokens out there. Now, let's cover a very important and actually it's a very nice feature in Solana, which it's called program derived PDA. What are these PDAs? You will hear and see them a lot in Solana. It's a very cool feature, if I may say, in Solana, because there are some sort of special accounts that your program that you write can create and control, which means that they are created in a way that they don't correspond to a private key because they are off the curve. When you generate a private key and a public key, you are on a curve, and then these PDAs are off the curve, so there is no way you can actually derive or, like, let's say, discover the private key for a PDA. And this is a very powerful feature, because especially for security, because not having a private key means there is no private key leakage, like you can leak the private key of a PDA, right? Because there is none. And another very important feature of the PDAs is that they are deterministic. They're deterministic. What does that mean? It means that their creation is known, like the parameters to create them are known, and every time you can derive the same PDA with those parameters. So there is no like nonsense or something else that can disrupt that. And the third feature, if I may say, is that they are owned by the program that creates them. So if you write a program for a marketplace and create some PDAs there, that marketplace program owns them, which means that that marketplace program can quote unquote sign transactions for that PDAs. They are very important feature, and it's a quite nice design, if I may say. Now, it sounds too good to be true. So now, when do you want to use these PDAs? Like, why not everything is PDA? Well, they also have some their drawbacks. But when do you want to use the PDA? Let's say you want to create a token account for each user, right? This is a special account called token accounts ATAs, and you'll see them a lot as well, because they are generated somehow automatically, and they have specific seed features. We're gonna see that in the next slide. You can also use PDAs to like store some program state. You want to store like a user profile settings or whatever. You can store them in the PDAs, and you'll know that only that program can actually modify that PDA data, nothing else. Like, you cannot modify those settings outside the program. Or for example, on an escrow setup, you are building some sort of like marketplace or lending up, and these PDAs can hold the tokens in this escrow securely, so you won't have any private key leakage or like accounts being leaked and those funds being drained, because only the program itself can actually release them. This is an important feature as well. Of course, you can write bad code that actually rugs them out from the PDAs, but that's another thing that is not Solana specific. Let's look a bit at the PDAs, right? And Anchor. Here, I am showing you an APAs, ATAs. These are basically associated token accounts, as I said, and they have a specific derivation pattern. As you can see, Anchor knows automatically that this is an associated token because it has this macro that says that this is an associated token for the mint, which is a mint that you specify as a parameter, and for the authority being the user that you specify again as a parameter. This address, ATA address, is basically derived from the wallet, like the user's public key, that being user. The token means public key, which is the mint. The SPL token program, because this is a token account and it's a SPL token account, right? And the associated token program ID, which is basically the program that creates this one, this account. So this is the only way you can generate this user ATA, which basically means that only this program can generate this ATA. And it's a very powerful feature, being also deterministic, because we use only these seeds. It means that you can always, even off-chain, compute this user at average, basically public key, if I may say. So you don't need to scan blockchain or like rely on the indexing to discover these seeds. No, they are pretty set in stones, and it's pretty easy to derive them. But this is just ADAs, right? Let's talk about custom seeds, because we also have, you can create PDAs with custom seeds. And if we look here at the user profile, we have these field seeds that let us basically specify what type of seeds we want to use to derive this PDA. If we look at the ATA here, we don't have the seeds. Why? Because, again, Anchor does this behind the scenes. Anchor knows that this is an ATA, and it knows how to calculate the seed based on these associated token specific fields. But when you want to create custom seeds, you actually have to specify, the seeds and the bump. They're very important. You can research them a bit more. There are a lot of things about how to save the bump and make sure that you cache it, so you can always derive the PDA safely. But I'm not going to talk about that right now. So as you can see, these seeds construct basically has a profile and a user key, and it generates this RTAM, which is this PDA, which is specific for this user. There is no other way to generate this PDA, because it's a user private key, so user public key, and this profile, which is basically kind of like a prefix that is we define in our program. No, it's okay. I'm almost half. Let's talk about another very powerful feature in Solana, and therefore also Anchor, which is CPI, cross-program invocation. Well, these CPIs are basically a way for the programs to interact. A program is deployed individually, so it does not have, if I may say, a way to call other programs without actually specifying that in the code. And how to do that? Well, we use these CPIs, cross-program invocations, which are basically a smart contract calling another smart contract in EVM, or a program calling another program in Solana. This is how modular design works in Solana, right? You write like a program that does something, and you have another program that does another thing, and then you can interact between them using CPI. When do you want to use CPI? Well, you use when you interact with standard programs, like SPR tokens, token 32 programs, because those itself have some written programs, so you have to interact with them using CPI. You can also invoke some system program utilities like the count or transfer solve by invoking some system program and so on, or even invoking custom logic from another program that you wrote or like someone else wrote. A very powerful feature, but also very dangerous, as we may see in the upcoming slides. This is for example, a CPI call to token transfer. So we are calling the token transfer using a CPI context. CPI context is the anchor, basically, is the anchor way of calling using CPI, because it lets you specify the program. Here we use the token program, and now we also specify all the accounts, if I may say, enforced, which is a from, right? The from is from where I want to transfer the tokens to, and the authority that controls the tokens, and of course the amount that I want to transfer. So this is a CPI behind this is a CPI call that calls token transfer in Solana. Well, I think this was kind of like everything related with Solana. As I said, it was just an intro for you to understand high level how we interact with the programs, how we create these accounts, what type of accounts do we have, and how we can rely on Anchor to build a lot of boilerplate behind the scenes, so we don't focus on that, and we just focus on writing the actual business logic for our application. But now let's see some, common bugs, pitfalls, because not everything is, secure. Let's look at the first bug that I want to highlight. We assume that a counter account was already initiated, right? So we don't talk about that in this slide. We have a counter account, data account, which has a count and an authority pub key, right? And we will try to increment. Now we have an instruction that wants to increment this account counter. And as you can see in the program itself, in the increment instruction, we just do context account counter that count and increment it to 1. At first, it looks like should work, right? Perfectly, no issue. But it actually it has a vulnerability, and the vulnerability usually is called fake account. What does this mean? It means that the counter account has no checks, so which means that it has the ownership check, which means, of course, that anyone can modify this account because there is not ownership check on this account, which means that whoever calls this, like the authority, can actually modify any type of account, counter account. How do you usually sort this? Well, you all actually has to specify in the macro that the counter, which is as an authority, has one authority. This has one authority means that whoever this field authority, which is the signer, must match the account data authority in the counter. So behind the scenes, the authority that assigned the transaction is matched with their account data authority. But this is all done behind the scenes, of course, by Anchor. But say a really simple piece of code, like a few characters, made a huge difference. Now I cannot modify any account that is out there. I can modify only my accounts. It's a very important it's a very important check. Let's go to the next one. The second one. Again, we have our counter, which now has one authority. But if we look at the authority, we see that now it's account info. Well, probably you already saw the issue, which is that authority account does not sign the transaction, which means that, again, an attacker can sign the transaction and specify any authority and their specific counter data account and increment it. So again, a missing check on the authority, which is it must be a signer, will allow an attacker to modify any account for the counter. In our this is just a disclaimer. In our context, like in my example, of course, there is no real damage, if I may say, but you have to extrapolate this and think how this can be exploited. For example, in in a lending platform, or like in an AMM and so on and so forth, where you can, for example, modify positions of random users if the specific checks are not performed. So how we can solve this? Well, it's simple. We just need to make sure that the authority is the signer, which means that whoever signs the transaction can modify its account. Again, a misinterpreted field in the Anchor made this code vulnerable. That's why I said Anchor helps you a lot, but by extrapolating a lot of boilerplate code and adding security checks and so on behind the scenes, but it does not protect you 100%. The third example, it's also interesting. We have an initialized instruction here. We initialize our counter account. And as you can see, we have everything here, right? We have has one authority, so I cannot modify any authority. So I can modify random accounts, right? And I initialize it. What it does is basically I initialize my authority being me, and I set the count to 0. But there is a small big issue here, which is the fact that I can initiate this over and over again, because there is nothing that stops me to initiate this account, right? Like I can then enter again on this account and just set the same authority and count to 0. This is because we are missing the init field, the init specification in the account macro. It's very important because it tells to Anchor that I need to initiate this account once. And if I try to initiate this account again, it will automatically fade. So I have to add this init in my counter account to make sure that this will initiate the account just once. Now let's play a bit more with this initialize. As we can see, the counter now is initialized correctly. It has an init, it has a pair, space, everything, and all the fields are set correctly. But now, in this specific instruction, I want to increment, which means that we assume that we want to call increment, but we don't care when the account was created. You know what I mean? We just want to perform increment on it. All because we have this init defined here, we are basically doing what is called DOS. Why this happens? Well, this happens because I can increment this counter just once if the account was not created. Due to the init, it will create it, and then it will let me increment it. But when I call this increment second time, it will fail because the account was already initiated. This is called the init DOS attack vector, and it usually happens when you want to initiate accounts, and but you initiate them when you perform a specific instruction. For example, in our case, we wanted to increment, and we initiate the account here. Usually, it's good to keep this initialize and specific instructions separate. Like you either initiate the account specifically via an instruction, like you open account or whatever you want to call it in your program, and then all the other instructions that are performed for that account can be, for example, written separately. Let's play a bit more. How do we solve this? Well, there is the easiest way is to use init if needed, which is another field in the account macro, which helps you circumvent this DOS. It will initiate this account only if the account was not actually initiated. And basically, right now, we actually solve this DOS, and the increment instruction will actually initiate the account only if it's not created. If it's created, it will actually ignore the init. Now let's talk a bit about a more complicated, let's say, issue with the BDAs. We have here two instructions. We have basically create a new product, which defines a new product with a name. And this product is basically a PDA that stores data. And we have a bid. So people can bid on that product. And every bid is created by using the product name and the user public key. And again, the bid is a BDA. If you look at it, it looks pretty harmless. Everything is checked. The Cs are actually unique because for every user public key, you have a product name. So they are quite unique. There is no way for this to interfere. Well, actually, that's not true because there is a caveat when you use the PDAs. The elements in the seed array, so these elements in the seed array are treated behind the scenes by the anchor as a collection of bytes. And they're processed in 32 byte chunks, which means that every field here is a 32 byte chunk. Therefore, here I gave an example of two PDAs that actually will collide. And an attacker can actually mine this for every product and specific users and block them. And by generating these basically fake products with these names will collide with the seeds for a bid. So in this way, an attacker, can DOS the user for placing bids on specific products. This is a pretty interesting attack vector. It has a slightly warning in the documentation, but it's a good thing to understand that the PDAs, while they are deterministic, they also mean that it can introduce some DOS if they are not used properly. The usual, let's say, way to solve this is to either add a third field that is, I don't know, incremental or index, where you can actually use this safely. The fifth attack, it's called the revival attack. These accounts can be also closed. What does that mean? Well, if you remember, when you create an account, you pay some rent, which is called, which is paid in lamp ports. Well, these are basically a way for you to create accounts, but you can also close accounts. How do you close them? Well, you just clean the data and transfer the lamp ports out. And Solana knows behind the scenes to garbage collect the account. The problem here, as you can see on the left, is that if an attacker creates this an instruction to clean the account, but also to send some lamp ports back to the account, Solana doesn't garbage collect, so the account is actually alive again at the end of the transaction. How do you sort this? Well, it's simple. Anchor offers a close constraint on the macro, which will basically safely close the account, send the lamp ports to the user specified here, and also add the discriminator to the account, and that account is marked as closed and cannot be revived again. These are actually some attack vectors interesting in the past that you can read about. I have just 1 minute, I think, less. Sorry. And I'm gonna just speak a bit about the unsafe CPI calls, because CPI calls offer so much, flexibility. It does not mean that they are safe. It's very important to understand how the CPI calls work, right? For example, in this one, if we don't verify the inputs, the CPI calls are very, very dangerous. In our case here, the destination is basically not verified, and the account set to the CPI call can be basically spoofed by an attacker, and you end up transferring the tokens to to a destination written by the attacker. Is this solve here? Of course, is to actually match this destination with a specific and expected destination key, which will solve this. There is another unset CPI call, which is basically not validating the program that you execute the CPI call on. In our use case here, we have the token program. As you can see, it is specified as an account info. It's not specified as a token account, as a token program, which means that an attacker can actually override this with a malicious token program, and in our case, drain this withdraw, because the token program will be a malicious one. There is another type of attack. Actually, not attack. This is more like a security issue when you deal with the tokens, because now we have SPL tokens and token 22s. The SPL does not support token 22 because it did not know about token 22 standard. So sometimes if you want to transfer tokens and you use the legacy SPL transfer, it will actually differ for token 22 standard. So to solve this, you just, for example, can treat the program as a generic, then just transfer using the CPI. It's a bit more complicated for this to be actually explained in one slide, but it's good to understand this, that sometimes, like transferring legacy SPL is not supported by the token 22. And for example, if you are you're building an AMM, and you want to support all types of tokens, you have to take this into consideration to support both standards. And of course, the last one, which I think is also good to end with, is the one that I cannot teach you about, which is the logic issues. And it's still the first security risk in Solana programs, which is the faulty business logic. And there is no tool that can actually help you this, other than just build these defense layers, which are code reviews, extensive testing, fast testing using Trident, or all types of tools that also for Solana. Of course, do security audits, and if you have enough capital, also do formal verification, because it's a very important also step, and defense layer. So all of these can actually somehow protect you against the logic issues. And I'm not gonna manage to go to the real world exploits, but I wanted to present just two, which was the wormhole one, which is quite interesting. By using a deprecated load instruction add function, the attacker managed to drain some good amounts of money, of capital. This is basically the deprecated function that was used. And the Casio one, which was basically improper account validation. If there is something I'm not gonna enter into details because I don't have the time, I apologize. But if there something I want to let you with and understand, is that Solana basically, besides this business logic issues, the other the issue that I discovered in practice is not enough validation. As we saw, we have a lot of validation that needs to be done in Anchor, and sometimes the team do not validate enough the account data, which will lead to attackers to circumvent those validations and actually exploit, unfortunately, the program. So please, if you have any questions, you can feel free to reach out to me. You have my X account, I think, in the event as well, and I'm happy to answer any question if you have I thought this presentation won't take that long, but it actually took 5 minutes more than expected. I apologize. I hope you stay safe and write secure Solana programs. And thank you for listening to me. Bye bye.